You gotta know a day. Today we're going to talk about linear momentum again. Remember, linear momentum is mass in motion. It's conserved in collisions like these beautiful collisions right here. But today I'm going to talk about obscure connections. It's going to be a little bit word association-y because the math gets really buck wild with some of these clues. So I'm going to bring up some theorems and then I'm going to get to some equations that are just going to kind of be word association-y. There are partial derivatives involved, and as such, I'm just going to give it to you. So the first thing is Noether's syndrome. Yep, that's right. It's pronounced Noether. And she was a mathematician who worked with symmetry. And basically said, if a system has symmetry, then there must be quantities that are conserved. And this can be applied to physics, where if we're talking about translation in space, or essentially the fact that physics laws apply everywhere in space, so a law everywhere in space is going to apply. Because of that, momentum is conserved. There's actually other things that are conserved due to Noether's syndrome, but they like to ask about momentum with Noether's syndrome because symmetry leads to conservation of momentum. There's also something called Heisenberg's uncertainty principle, and this applies, especially he worked with electrons, and basically the more you know about the position of a particle, the less you know about its momentum. Again, its mass and its velocity. And vice versa. The less you know about the position, the more you can know about the momentum of the particle. This equation here applies. You're going to see h several times today. That's Planck's constant. But again, these are uncertainty in position. The greater this goes up, then this has to go down, and the greater this goes down, this goes up. That is Heisenberg's uncertainty principle. Now we're getting word association. There's something called a momentum operator, and it is equal to negative I, that's the imaginary I, times h bar, which is the reduced Planck's constant, times the gradient. Momentum itself is equal to the derivative of the Lagrangian, again, complicated math, with respect to velocity. That's what this symbol is here. And finally, we're going to talk about the de Broglie wavelength. We've talked about it a little bit in the past in past videos, but essentially, the de Broglie wavelength is the wavelength for a particle, and it states that it's equal to h, Planck's constant, over momentum, which again is mass times velocity. But Planck's constant over the momentum of a particle is going to be equal to its wavelength. So that is more obscure mentions of momentum. It's very likely that these would be very early clues for momentum.